Okay, in this video, I'll walk you through several examples on estimating confidence intervals. So let's start with a scenario when the population standard deviation is known. So remember, sigma is our population standard deviation. So if the population standard deviation is known, then we want to go with the z distribution. So let's say this quick example. A researcher wants to estimate the mean systolic blood pressure of 17-year-old females in Arkansas. The population mean is unknown, but the estimated standard deviation of the population is 12 millimeters of mercury. And so the study took a random sample of 16 girls and found their mean blood pressure to be 113 millimeters of mercury. And the goal here is to compute a 95% confidence interval. So what information do we have? So first, we don't know what the population mean is. And the goal of the confidence interval is to estimate the plausible values for this population mean. Our goal here is to estimate this guy. Okay? So what other information do we know? So we know that the population standard deviation is 12 millimeters of mercury, and we know the sample mean to be 113 and the sample size was 16. So the best guess, so the question below just says what is the best guess of the population mean? So our best guess here is the sample statistic, which is 113, but it doesn't mean that 113 can replace the population mean, right? So that's why we want to create a range of plausible values that we think the population mean is. Okay. So now here I just make a note here. We only have one variable, which is the systolic blood pressure, and the population standard deviation is known. And since we know the population standard deviation, then the one sample z statistics confidence interval is the most appropriate for this scenario. So this is what the formula looks like. So we know m is a sample mean plus or minus the critical value times the standard error. And using your z table, the critical value for the 95% confidence interval is 1.96. But the good news here is that for the z distribution, this critical values is the same. So whenever you want to compute a 95% confidence interval and you're working with z, then this is always going to be 1.96 for 95%. Okay. So now let's compute that confidence interval. So the sample mean is 113 plus or minus the critical value for 95% confidence interval times the standard error, which is 12 divided by the square root of 16. 12 is the population standard deviation and 16 is the sample size. And now, so we have 113 plus or minus the margin of error. So the margin of error here is 5.88. So 5.88 is our margin of error. So I want to add and subtract that from the sample mean. Okay. So and that leaves us with a confidence interval of 107.12 and 118.88. So we can say that the mean blood pressure of our population of 17-year-old females in Arkansas is between this value. So the range of our unknown mean value is within this range of values. Again, this is just saying this your critical values are pretty constant for the z distribution. So how would we interpret this confidence interval? So this is the confidence interval we calculated in the previous slide. So you would say we're 95% confident that the mean systolic blood pressure of all 17-year-old females in Arkansas is between this value and this value. Or you could also say here, what I did here was I used all here, or you could also use true or population mean. So we are 95% confident that the true mean systolic blood pressure of 17-year-old females in Arkansas is between this value and this value. So you could use all, or true, or the population mean, whichever one you're comfortable with. Okay. So now let's talk about another scenario when the population standard deviation is unknown. So remember, when the population standard deviation is unknown, then you would use the t distribution. Let's see the scenario. So the university administration wants to estimate the average amount U of A students spent on textbook last semester. So a random sample of 25 students was taken, and the sample mean spending on textbook last semester was found to be 305 with a standard deviation of 65. So here we want to compute a 95% confidence interval to estimate the average amount U of A students spent on textbook last semester. So what information do we know? So we don't know what the population mean is. That's the whole goal of confidence interval, because we want to estimate this population mean. We also don't know what the population standard deviation is. And we know this other information. We know the sample means, we know the sample standard deviation. We also know our sample size. So from there, we would use the one sample t statistics confidence interval to solve or to calculate our confidence interval. So this is what the formula looks like. So the only difference here is that we're working with the critical value based on the t distribution, and we also done we're working with a sample standard deviation, which is s. So remember, the first thing you want to do is to find this critical value, which is also called multiplier. So your critical value is based off the degrees of freedom, which in this case is 24. So you would go to your z table, which is what we have here. So you go to your z table, go to two-tailed, because confidence interval is two-tailed. And for 95% confidence interval, you would look for 0.05. Because remember, 95% confidence interval corresponds to 5% significance level. So you would look for 0.05. And our degrees of freedom is 24. So 24 here, come all the way and find where it intersects with 0.05. Remember, this is going to be two-tailed. Don't go with one-tailed. So our critical value is 2.064. Okay. So that's where this 2.064 comes from. So now to calculate our confidence interval, it would be 305 plus or minus 2.064 times 65, which is our sample standard deviation, divided by the square root of 25. And that leaves us with a confidence interval of this range of values. Okay. So this is our confidence interval. So how would you interpret this confidence interval? So you would say we're 95% confident that the mean spending on textbook by all U of A students last semester is between $278.17 and $331.85. So if you notice, this is our range of plus. So we are just saying that we think the true mean is between this range of values, and we're pretty much confident. We're 95% confident. Or you could also replace the all with true, whichever one is fine. So confidence intervals for independent samples. So independent samples, remember we did this even with hypothesis testing. We have two groups, and our two groups are independent, and we are measuring a quantitative value from those two groups. So let's see an example. How many flip-flops do you have? How many flip-flops do I have? I think I have 4 at the moment. Yeah, I do have 4 at the moment. So, in a survey of statistics for nursing students, an instructor asks her student how many flip-flops they have. The instructor intends to estimate the difference between the number of flip-flops by student sex. So for female and male students, the instructor asks them the number of flip-flops they have, and they have, in this study there are 31 female students, 31 male students, and the mean number of flip-flops female students have is 6.22, and the mean number of flip-flops male students have is 2.54, and this is a standard deviation of the number of flip-flops that they have. Okay, and our goal here is to compute a 95% confidence interval for the difference between the number of flip-flops male and female students have. Okay, so what information do we know? So we know the sample mean for the male and the female. We know the sample standard deviation for the two groups as well, and we also know that 31 males and 31 females were sampled for this particular study. And how would we compute their confidence interval? This is the formula again. You could the good news is confidence interval. You could do the male minus the female, or do the female minus the male. It doesn't matter what direction you calculate or what direction you go. So this is MF minus MM, then plus or minus the critical value, then times the standard error of this statistic. So how do you find your critical value? It depends on the degrees of freedom. So degrees of freedom is the sample size for the female, the sample size for the male, and minus 2. So 31 plus 31 minus 2 gives you 60. Then you go to your T table again. You can pause this video and check that you have 1.671 as your 90% confidence interval, critical value for the 90% confidence level. So remember, the 90% confidence level is corresponds to 10% significant level. Okay, so plugging all these values that we have, we found our confidence interval to be values between 2.30 and 5.06. So just for something for you to note, so remember 2.3 here is a difference between the number of flip-flops male versus female students have, and 5.06 is the same difference. So this is just saying the difference, the range of our plausible value for the population parameter, which is the difference between the number of flip-flops male and female students have, is between 2.3 and 5.06. So how would we interpret this confidence interval? So you could say we're 95% confident that the differences in the true mean number of flip-flops of female students compared to male ESRM students is between 2.3 and 5.06. Or another very intuitive way of interpreting this confidence interval is that we are 90% confident that the true mean number of flip-flop female students have is between 2.3 and 5.6 higher than the male student. This just makes sense because this is saying the difference between what the females have and the male, female minus male, is between 2.3 and 5.06 higher than this other group. So let's compute the confidence interval for the dependent sample. So remember, the dependent sample, it could be pair design by repeated measure, where you measure someone twice, or pair design by matching. So when we have a scenario, let's read this question. How fast do newborns grow? So a study was conducted to assess how fast newborn babies grow. A sample mean of 20 newborns were taken. The heights in inches of the newborns were recorded at birth. After 7 days, the heights of the babies were again recorded. The summary statistics is presented below. And in this example, we want to compute the 99% confident interval. So these babies, 20 babies were measured at birth, and after 7 days, the 20 babies were measured again. And our goal is to estimate the difference between the growth between at birth and after 7 days. So to compute a 95% confidence interval, you would use the formula for, so just replace your statistics with MD, then plus or minus the critical value times the standard error. So remember your critical value again, the degrees of freedom is 20 minus 1 because our sample size here is 20, which is going to be 19. and we're computing the confidence interval for 99%. So you can pause this video again and go to your t-table to check that you have a critical value of 2.861. This is very important, especially if you have to work on your homework assignment where you have a bunch of questions on confidence intervals. Okay. So in computing this confidence interval, you would use the mean difference, 1.2 plus or minus the critical value times the standard error, and you would find that the confidence interval gives you a negative 0.053 to 2.93. Okay. So how would we interpret this confidence interval? So you would say that we're 99% confident that the true mean difference in height of babies when they were born and after 7 days is between negative 0.053 and 2.93 inches. Okay, so we would pause here in this particular video, and the next video will just walk you through some important factors about confidence interval, and that will be the last video on confidence intervals.